These days, all of us are used to this one experience when it comes to deploying our applications, which is just click on a button to connect your GitHub repository, then selecting whatever the code repository that you want to deploy, which is in this case next demo. And the branch is, of course, we want to deploy the main branch. And we just check this automatic deployment on any commits to the main branch. And we just go ahead and select a plan, which is the free plan, and we click on deploy. And then the build starts, and we can see in real time all the commands that are running in our server, how the server is actually deploying our application. And in a few minutes, our deployment is finished, and we can just click on this button and visit our app live on the internet. We went from raw source code to a live version of our app in a production grade infrastructure in just 2 clicks. This whole experience is enabled by platform as a service providers like Sevalla and Heroku and Netlify, Vercel, all the platforms that we know today. And the moment you push a new change into your branch, or the moment you configure a new repository and click on deploy, between that click and when your application is ready to be visited over the internet, in those 2 minutes, a lot of infrastructure effort goes on behind the scenes. So in this video, we'll explore the origins and how we came from manually configuring servers and all the infrastructure related changes by hand to this whole smooth experience of platform as a service. We'll also understand all the technical parts, how and what are all the things services like Sevalla and Heroku and all the other providers that we know today work behind the scenes. What are the tools they use, what are the workflows they use, and how it all comes together, so that we can appreciate the technology a little more and we can understand it a little more. So let's start with a bit of history so that we understand better, we appreciate better all the things that we are coming from, all the shortcomings that we have overcome over the years and where we are exactly today. So the core problem that we are trying to solve is we have code in our local and we can run the code in our local, but the code needs a place to run so that it is accessible by people from all over the internet. That is our core problem. Now, coming back to the history part, for decades, or as long as we have been programming, all the programmers face the same problem. How do you actually take a brilliant idea that is living in your mind, transform it into a working software, and then make it available to the whole world? And the answer to that lies in servers, configurations, operating systems, network settings, security patches, and 1,000 other details that had nothing to do with the actual problem that you were trying to solve. And then someone asked the question, what if we could make all of that complexity just disappear? You just focus on your code, you just focus on your idea, you implement that, and all the complexities, all the servers, configuration, security, and domains, traffic, everything is abstracted out by a single platform. And that is the idea of platform as a service, a technology that transferred not just how we build software, but how we think about the relationship between human creativity and digital infrastructure. And it is a story of the last 2 decades, from a small experiment in 2006 to a global industry worth 185 billion by 2032. So let's just jump into that story. The year was 2006 and iPhone did not exist yet, and Facebook was still limited to a few college students. Amazon Web Services had launched with a simple storage service called S3, and Google was primarily a search company. And when someone mentioned the word cloud, people only thought about the weather, not the kind of cloud that we talk about today. And in this particular world, in the world of 2006, a company called Potango, which was owned by Canon Europe, they launched something that would completely change the trajectory of the way we build software today. They launched a product, and the product was named Zimi. And This product called Zimki, this was the very first attempt at the technology that we call as platform as a service. So the problem Zimki was trying to solve is this. What if you could write your entire application in JavaScript, deploy it with a single command, and pay only for what you use? And what if servers, databases, and operating systems could simply disappear from the developer's mental model, and developers only focus on the code part? So in Zimki, each application ran in its own isolated container, even though the container technology that we know today, which got famous because of this particular technology called Docker, that did not exist for the next 7 years. We are talking about 2006, and Docker came around 2013 or so. But the idea of containers, the concept and the technology of containerizing, that still existed. Docker did not invent the concept of containers. We already had this concept of containers called LXC, Linux containers, which used Linux C groups and namespaces for virtualizing software. And years later, Docker actually built on top of LXC to make this whole workflow of building and creating and running containers more accessible to the mass users. But the technology containers, they were always there in the form of LXCs. And this product Zimki, it used isolated containers for each applications to provide a very good security model. And the users who use this platform, they paid for actual CPU cycles and memory usage and those kinds of metrics which directly related to the usage and the consumption of the computing resources. And that particular billing model was very revolutionary, because until then, all the servers, all the hosting setups, all the VPS and all, they were charging based on how long you are renting the servers, based on a completely different metric. It did not matter how much your usage was, as long as you are renting a server, as long as you were renting a VM, a virtual machine, you still paid the same amount. And this particular billing model where you paid based on your usage, that was the very first revolutionary step into this kind of billing model. But today, this kind of billing model is very popular, especially with the technologies like serverless. If you use platforms like Vercel or Sevalla, these platforms, they also charge you based on your usage, not based on how much servers you are renting and how long you are renting it for. And Zimki ran very successfully for the first 18 months, but the technology worked, but the business model, the business environment did not really support it. The developers were skeptical of putting their applications on someone else's infrastructure during that time. And enterprises, of course, were very uncomfortable with the lack of control. And the most important part was Canon made a strategic decision in December 2007, and cloud computing was not part of their core business focus. And that was the reason the platform Zimki was shut down with the 30 days of notice. Every application built on Zimki disappeared overnight. Developers lost months and years of work. The code was trapped in a proprietary system that no longer existed, and there were no migration tools or export capabilities, and no way to recover the intellectual property that had been built on the platform. And that was the first time developers who had built their ideas, their applications on top of Zimki learned a very harsh lesson, and that is still popular today. And we call that phase as vendor lock-in, which basically means being very so closely coupled to the vendor, to a service that you use, that if that service goes down, you go down with them, or at least you get affected so much that it shows up in your revenue, in your customers, etc. Even though this whole story of Zimki was a failure, that was still considered a revolution. And that's where a lot of successful ideas of platform as a service was born. Which brings us to our next story, which happened in the year 2007, where 3 programmers were working on this particular project, which is called Heroku. Heroku, one of the most influential and revolutionary platform as a service providers even today. but Heroku is the one that started it all. Even though Zimki was the one which introduced the idea, introduced the concept, but Heroku was the first successful attempt at the whole platform as a service provider business model. They did share Zimki's vision of deployment simplicity, but they also learned from its downfall why it failed. So instead of creating a completely proprietary system, they built on open standards, open source standards. Instead of locking developers into a single language like JavaScript, they supported multiple programming environments. And instead of hiding the underlying technology completely, they provided abstractions that developers could understand, they could debug, and they could have some control over. Heroku introduced the world the 5 words that would completely change the way we build and deploy our software today, which was this: git push Heroku main. This is all it took to take your source code and deploy it in a production grade infrastructure setup. There was a very sophisticated system behind these 5 words, and the system which could take your application code, analyze its dependencies, compile it into an executable package, deploy it to a distributed infrastructure, and make it available to users around the world over the internet with just one command. They made it possible with a container technology called dynos, which are kind of a lightweight containers, even though the mainstream containers that we know today, Docker, that arrived around the year 2013, but we are talking about 2007 here. So dynos are kind of a lightweight containers. There were different kinds of dynos. For example, there are web dynos. Web dynos, they handled HTTP requests that were coming from the users. They also had worker dynos, which were used for processing background jobs like sending emails, sending notifications, or generating reports. There were also one-off dynos for performing one-time tasks like database migrations or some script that you run as an administrator, etc. So different kinds of dynos were introduced for different kinds of jobs that an application might need to perform. And with this setup, developers did not need to understand Linux containers or process management or load balancing. They just needed to understand dynos, which mapped pretty naturally to how they thought about application architecture. So a web application built with this process in mind, it just became a collection of web dynos placed strategically behind a load balancer. The tasks like background processing, they became worker dynos, which consumed from message queues. And the complexity of distributed system was completely hidden behind concepts that matched developers' mental model. The system, the sophisticated system that went behind it was the technical implementation of this whole thing, the dynos and the Heroku's deployment pipeline. It was pretty sophisticated, even by today's standards. They had something called a slug compilation, which basically created a compressed and pre-processed application copies through multi-stage pipeline. And the system would create a fresh checkout of your application code every time you wanted to deploy. And it would install all the dependencies using language specific build packs. Now, build packs is important in this context. We'll come back to what are build packs. But this was something that was introduced and it was invented by Heroku itself. But we still use it today. Pretty much all the platform as a service provider use this particular tool. It's called build packs. We'll come back to why it matters and why it is so important. It would install all the dependencies using language specific build packs, and it would compile all the assets and binaries if it was necessary for that programming language. And it would package everything into archives and store that in Amazon S3 or any other object storage. But S3 was pretty popular then, so S3 was what they went with. These slugs, they could be deployed instantly to any number of dynos without repeating the whole compilation process. They also had very good support for networking to connect different nodes together. The Heroku router, they had a routing infrastructure that could distribute all incoming requests across thousands of dynos, and the router will handle things like SSL termination, connection pooling, and automatic failover, things that developers used to configure manually at that time. The system also tracked the health of the dynos and automatically removed the failed instances from the load balancer rotation. That was about Heroku. And around the same time, when Heroku was building this, in 2008, Google came up with something which is called the App Engine. Google App Engine, they launched in the year 2008, and they brought platform as a service to mainstream attention. Until then, only a selected number of people knew about them. But when Google introduced its technology, Google App Engine, which was the first mainstream platform as a service provider, that's when it was subjected to the mass adoption. Even though Heroku focused on things like simplicity and flexibility, Google's App Engine, it offered something that was almost impossible around that time, which was unlimited and automatic scaling. And it was able to provide that unlimited automatic scaling because App Engine made a different trade-off than Heroku. In exchange for automatic scaling that could handle millions of requests without developer intervention, applications had to work within strict constraints. The developers could only use a certain programming languages. Initially, it was just Python, but later on, Java, PHP, and Go also got added to that list. They had to store data in Google's proprietary data store rather than traditional relational databases. They couldn't write to the local file system or make arbitrary network connections or run processes that lasted longer than 30 seconds. All of these constraints were definitely limitations, but they did provide something that beat all of it, which is automatic scaling from 0 to millions of users without any infrastructure changes. And that fact was pretty revolutionary around that time. The App Engine runtime, it could automatically create new instances of your application when the traffic of your users increased, and it could automatically shut them down when the traffic decreased. Developers only paid for actual CPU cycles and the actual amount of storage consumed, and with no charges for idle capacity. And after that, more and more platforms showed up. For example, Force.com from Salesforce, or Engineered with its Ruby and Rails support, etc. etc. So then came the container revolution. The early platforms of 2007 to 2010, they proved that abstraction could simplify deployment without sacrificing power, but they also revealed new problems. Each platform as a service provider, they used different deployment mechanisms, different configuration formats, and different runtime environments. Applications that were built for Heroku, they could not be easily moved to App Engine, which was by Google. And the code that was optimized for Engineered, which provided good support for Ruby and Rails, they would not work on Force.com, which was another platform as a service provider. So the problem was pretty clear. The industry needed standardization, and that particular standardization came in the format of dependency management. In 2011, Heroku invented something called build packs that we still use today. It is very important in pretty much all the platform as a service providers workflows. So a build pack at that time, it was just a collection of scripts. You can imagine a couple of shell scripts, if you have seen them, that will examine your application code when given to them. They will figure out what particular language and framework your application code used, and they will install all the necessary dependencies and package everything into one deployment unit, and it will be called a slug. The whole build pack workflow, it worked in two phases, and this whole two-phase based workflow we still use today in pretty much all the platform as a service provider workflows. It has become kind of an industry standard for deploying applications for consumers. But in the first phase, it is usually detect. A detect script, it will examine the application code and it will determine if the build pack is appropriate or not. For example, if your application had a package.json, then the Node.js build pack will claim the responsibility of building your application. Similarly, if your application had a file called requirements.txt, which is typically present in Python projects, then a Python build pack will take over and it will take the responsibility of building your application. Similarly, if it had a gem file, then the Ruby build pack will handle it. And the second phase is build or compile. The compile script will basically install the dependencies, compile code if necessary. For example, some programming languages, they don't need to be compiled. For example, JavaScript, Python, but languages like Go, they need a proper compilation step before they can be run. And finally, it will prepare everything for execution. For example, if we are talking about a Node.js application, if your application is a Node.js based application, then the script will run npm install, npm space install, so that it can install all the dependencies of your application. It will fetch the dependencies from the npm registry and it will install it. Same way, the Python build pack, it will create a virtual environment. If you are familiar with how Python applications are run and used, they are usually run inside a virtual environment. And to install the dependencies for a Python project, we run something like pip install. We have modern installation tools like UV now, but pip is still the standard. Similarly, the Ruby build pack, if you have an app which uses Ruby on Rails, it will install the gems using bundler. Each language-based build pack, for example, Node.js build pack, Python build pack, Ruby build pack, each of these build packs, they encoded the best practices for deploying applications in that target language. So the Node.js build pack will have all the best practices of how to properly deploy a Node.js app into production to squeeze out the maximum amount of efficiency and optimization. And this whole two-phase deployment system, this pretty much became the industry standard for dependency management, because it solved a problem that had plagued deployment for years, which is how do you automatically figure out what an application needs to run and how do you install all those dependencies reliably across different environments and different operating systems. That was the core problem a build pack based workflow completely solved. And that's why it is still an industry standard even today. Heroku also created an ecosystem where third-party build packs, they could provide specialized support for new languages, frameworks, and deployment patterns that Heroku itself cannot maintain, because there are like infinite number of frameworks and languages if you start counting. But finally came a revolutionary technology, which is Docker. Now, as I said earlier, Docker did not really invent containers, but it definitely made them accessible to ordinary developers. Because before Docker, if you wanted to work with containers, if you wanted to create, manage, and run containers, since containers were a very complex Linux feature that required you to have a very deep knowledge of system administration and knowledge of how to manage namespaces, C groups, and file system layers. Developers who dealt with application code, who wrote normal programming languages, they did not really get into this whole container part. But with the introduction of Docker and the more simplified workflow of managing, creating, and running containers, pretty much in no time, every developer was using Docker. Because this is how Dockers work. You just write a very simple text file, which is called a Docker file, which will have a content very similar to this that we have here, which is a Python-based application image building. And you just ran Docker build, which will create an image, and you just run Docker run, which will start the container. And now your application is running. This whole file format where you take a base image, you define your working directory, you copy whatever you need into the Docker image, and you start your application. This is pretty intuitive, and you can just spend an hour or two and you will have enough understanding about Docker and Dockerfile that you can start working immediately. And that made a huge impact on developer adoption and introduction of Docker in many workflows. With the introduction of Docker and Docker being mass adopted by developers, containers turned out to be more useful than VMs. So before this, a lot of platform as a service providers, they also implemented VMs, virtual machines, in their workflows instead of containers. Now, the difference between containers and virtual machines is they both are definitely virtualization technologies. They do provide abstractions on top of a host operating system. But the difference is containers, they share the kernel of your host operating system. But virtual machines, they abstract out even the hardware part, even though it is virtual hardware, but they still abstract out every single component down to the root level. And that is the reason virtual machine, they offer more security at the cost of being more resource heavy. On the other hand, containers are pretty lightweight since they share the kernel of the host operating system. But when you have security requirements, which is very strict, you should definitely opt for virtual machines. But again, for this particular use case of running your application on top of a host operating system and your containers being portable, this suited very much, especially in the context of platform as a service, because this meant that a single server could run many containerized applications as compared to the number of virtual machines, which reduced costs and it improved resource utilization. But the most important thing about containers and about Docker was it gave developers a standard way to package applications that would work across different platforms. A Docker image that you built in your local system, in your Windows or Mac or Linux, any other operating system, that could now run on AWS, Google Cloud, Microsoft Azure, or any other infrastructure that supported container execution. And this whole feature of portability, it reduced vendor lock-in and it gave developers more deployment options. And that is the reason the whole platform as a service industry, it started quickly adapting to the container revolution. Heroku, it modified its whole build pack workflow to generate Docker images at the end of the workflow instead of generating slugs, which was a completely different packaging and portability solution as compared to containers, which is not very efficient. The whole slug compilation process, it remained the same from a developer's perspective, but the output, instead of becoming a slug, it became a standard Docker image that could run anywhere now, which solved the problem of portability. Same way, OpenShift, which is the enterprise platform of Red Hat, they completely rewrote their architecture around Docker containers. Their previous version, it used a proprietary system called Gears, which is for application isolation. But OpenShift v3 in the version 3, it was completely rebuilt entirely using Docker and Kubernetes. Same way, Cloud Foundry, another platform as a service, they took a completely different approach. They developed their own container runtime, which was called Garden, but they did maintain the compatibility with Docker images. Now, Garden was specifically designed for the Cloud Foundry architecture, and it provided features like rootless execution and resource limiting that were not available in early versions of Docker. And that was the reason Cloud Foundry, they developed their own container runtime, which is called Garden, while maintaining the compatibility with Docker. Now, with the adoption of containers, it solved the problem of portability, basically the problem of it works on my machine. But then came the next challenge, the next problem, which was how do you actually manage hundreds and thousands of containers across hundreds of servers? It's not necessary that all your containers will be inside a single server, since we are talking about distributed systems. So that was the new challenge. How do you actually manage all those containers that are spread, that are distributed across different servers? So with this challenge, the clear solution was obviously an orchestration platform, and a couple of orchestration platforms were introduced. For example, we had Docker Swarm, then Apache Mesos, and then Kubernetes, which is from Google. Kubernetes, it originated from Google's internal container orchestration platform called Borg. So before the introduction and creation of Kubernetes, Google internally in their own workflows, in their own company, they were using this container orchestration platform called Borg for the last decade, for the last 10 years. before they open sourced it in the form of Kubernetes. And they made Kubernetes available to the general public in 2014. But the problem with Kubernetes was it was not designed for simplicity. It was designed for power, it was designed for flexibility and enterprise requirements that a company with the scale of Google might have. It had dozens of different resource types, complex networking models, and intricate configuration requirements and operational complexity. The learning curve of Kubernetes was pretty steep. Developers needed to understand pod services, deployments, ingress controllers, persistent volumes, config maps, secrets, namespaces, dozens of other concepts before they could deploy even a simple application. The configuration format, which was YAML, it was pretty verbose and it was error prone. And the whole networking model, it required the understanding of cluster DNS, service discovery, and load balancing. But for platform as a service providers, Kubernetes offered a lot of capabilities. It could automatically schedule containers across a cluster of servers. It could restart failed applications. It could roll out updates with zero downtime. And it could scale applications based on CPU usage and custom metrics. Then later on, platforms like platform.sh, they introduced what we know as the Git based workflow when it comes to our deployments that we follow so extensively today, that we are so used to today. They were the first ones that introduced this whole Git driven infrastructure format. Then we had platforms like Railway. They invented this new format for dependency management called Railpack. And later on, they also introduced a format called Nixpacks, which is currently, as per the industry standard, the most optimized, the most efficient format for dependency management, the whole detect and build pipeline, as compared to the traditional build packs introduced by Heroku. But most platform as a service providers these days, they have compatibility for all these different kinds of dependency managements. For example, build packs, rail packs, Nix packs, among other things. Okay, with that amount of history, I think it is time to get into the technical part, which is how exactly and what exactly these platform as a service providers like Sevalla or Netlify, Heroku, Vercel, Railway, Render, all these platforms, what exactly they do behind the scenes, starting from when you push a commit or when you select your repository to providing a domain so that everyone can access your application on the internet. What exactly happens? Now, the exact steps that all these platforms do, that might differ, because of course each platform will have their own workflows, their own optimizations. But assuming the standard way a platform as a service provider that I will build today will explore what are the workflows we will need to build for it to work properly. So before we get into the individual workflows, individual parts and phases of the whole workflow, let's just sketch out the overall things that we will need to do, which will start from a git push. From there will be a webhook call from the GitHub side. Then we have to queue. A deployment job will be pushed into a worker queue, and we'll discuss why it is pushed into a queue after this. Then we have build and container, this registry push to Docker registry. Then we'll reach an orchestration step, which is either going to be a Docker swarm or a Kubernetes based orchestration. And in the end, we have things like domains and reverse proxy, SSL certificates, and traffic routing. So on a high level, we can trace the steps starting from a typical git push or connecting to a repository, then GitHub triggering a webhook call, which will trigger the platform that we are using for deployment. Then that platform will create a deployment, push that into a queue. Then a worker of that queue will pick up that job. It will build the container, push the container into a registry, either a private registry or registry that you have configured to push images to. then it will, then a orchestration platform, then an orchestration platform like Docker Swarm or Kubernetes will take over so that they can add the new containers, they can properly route traffic to the new containers, and they can monitor the new containers. Then in the last step, we'll introduce a reverse proxy, something like Traffic or Caddy or Nginx, whatever with the most features that will handle our domains, our SSL certificates, and finally traffic routing with load balancing. This is an overall map, what exactly happens. But now let's focus on each step, how and where it starts and how and where it ends exactly. Now, coming back to our Sevalla interface, is a platform as a service provider that we have been talking about for the last 1 hour. The first step that starts is from here, the user authentication and authorization. You want to give this platform, since we are following a Git-based infrastructure workflow, you have to provide permissions for this platform so that it can access a repository that is hosted on your version control system. This can be GitHub or GitLab or Bitbucket or a self-hosted instance of Git, whatever the famous version control system that you are using. That is the first step. After you give it your permission, then this particular provider, in this case, it will install a bot, an application, a GitHub application in your repository. Now it depends whether you want to give access to all your repositories or some limited repositories. In this case, I have given access to this one particular repository, which is Next Demo. When you give this particular application with Kinsta, again, Sevalla is a product of Kinsta. That's why we are seeing Kinsta here. But the point is, after this application, after this GitHub application or bot is installed in your repository, now it has a few permissions to access code, metadata, and packages. And it has also access to deployments, environment, and pull requests for this particular repository. Now, this is an important step because using this particular app, they will acquire a token, some kind of authentication token, and using that token, they can pull code. They can download our code, which is hosted in this particular repository that we gave access to this particular application. And they can also configure some webhooks so that every time we raise a particular pull request or every time we push something to our main branch, that webhook will be triggered, and that in turn will trigger the application, and that application will in turn trigger their platform, the platform Sevalla that we are using, and that will start a new deployment. And that is the first step of many steps that we are going to follow from this trace. Now, coming back, since we gave permission to the particular app, the GitHub app Kinsta, to have access to this particular repository, now we can select this particular repository, and whenever we push something to the main branch, then it should again get deployed. This is where our workflow with a platform as a service provider starts. The first step is user authentication and permissions that we have already done. Then comes the second step, which is trigger deployment. Now, this deployment can be triggered in two ways. The first way is which I just showed. This is your first time you are creating an application in Sevalla and you want to create a fresh new deployment, the first deployment for this particular application. So that can be one case where it can trigger a deployment, or once the first deployment is over, you have configured the provider to detect changes whenever we push something, whenever we merge something into the main branch, then trigger a deployment in that case. Then again, that can be another cause of triggering a deployment. So there are two instances where a deployment can be triggered. And once the deployment is triggered, we reach step number 3, which is a new deployment instance will be created. And this particular instance will have a lot of data. In the UI, we might not see all the data points that this deployment has, but it will contain a lot of data points like which is the region that we are deploying, what is the memory limit, what is the CPU limit, what is the plan that this user is on, and hundreds of other data points that a platform as a service provider will have to track to provide a controlled, a safe, and an efficient experience to the users. But we don't have to worry about that. We are just trying to understand the whole workflow on a very high level. So we can just assume that it creates a new deployment instance. You can imagine it as a new entry, a new record in their database, a new row in their database. That is a new deployment. And after a new deployment is created, then what they do, they push into a queue. Now this queue can be of different types. It can be a queue managed by Redis PubSub, a Redis queue, or it can also be a RabbitMQ queue, right? The underlying technology does not matter. We are just trying to understand the workflow here. And the reason a deployment is pushed into a queue is because all these background queue or background worker processors, they have a lot of features. Features like retry mechanisms based on exponential backoff and concurrency control, which basically means how many deployment jobs can be processed at a time, which is determined by the concurrency parameters. They also have features for congestion control. If too many deployments are triggered, then how to orchestrate them, how to manage them in a more efficient way, in a more controlled way, and a lot of other features that a queue-based workflow provides. So instead of just making an API call or just triggering a deployment job in a synchronous manner, we create a deployment and we push that into a queue so that it functions and it executes in a controlled manner, in a more robust manner. And after it is pushed into the queue, after some time, depending on how many jobs that we are currently processing, what plan the user is on, we control how many concurrent jobs they can trigger, how many times in a day they can trigger, and depends on what are your offerings are. But typically after we push the deployment into a queue, after a few seconds or a few minutes, it gets picked up by a worker processor, which will basically take all the information, for example, the deployment ID, the user ID, and what all information it needs to perform, to execute the task. So the worker finally picks up the job from the deployment queue, and then it starts processing. Then we finally come here when we actually perform steps so that we can deploy our application into a server and we can expose it over the internet. The first thing that might happen is, since we have already authenticated with our version control provider, either GitHub, GitLab, Bitbucket, whatever, the platform as a service provider, they have the token. They have the token to our VCS, which is the version control system. And using that token, they can run a command, something like git clone or whatever, with depth as 1, which basically means that instead of downloading all the commits starting from your first commit up until now, which can be for large open source code bases, it can be hundreds and thousands and millions of commits even. That's the reason when you're cloning a GitHub repository, if you pass depth 1 or depth 10, it will only fetch the last 10 commits, the last 10 recent commits of your repository, so that the cloning process is faster, because the provider only needs to deploy the last recent change. Now this happens if your deployment is a Git based deployment, which basically gets triggered every time you connect a repository or push something to your main branch. But platform as a service providers, they also provide options to deploy from a Docker image, right? For example, in this Sevalla interface, you can also mention a Docker image, which you want to deploy as an application. In that case, if it is a public Docker registry, they will pull it from there. If it is a private registry, from your authenticated credentials, they'll be able to pull that image from a Docker registry. Now at the step number 6, they have access to the code that they finally want to deploy in a particular server. Then comes the important step, which is build step. Now in this step, as we already know, we have different dependency management workflows which we have already talked about. We have build packs, which is from Heroku, and now it is part of the Cloud Native Foundation, the open project. We also have Docker. Then we also have Nix packs. Nix packs is basically another dependency management and build system, which was introduced by Railway, and it makes use of the Nix ecosystem to make the whole dependency management workflow more efficient and a little faster. And these days, Nix packs is the industry standard when it comes to dependency management from platform as a service providers. In fact, if you go to the documentation section of Sevalla, they offer 3 different types of build options. One is Docker file, then is the Nix packs, which is from Railway, and then we have build packs, which has very good compatibility from Heroku, because they are the ones that invented this whole build pack system. But by default, most of the platform providers, they make use of Nix pack, since it is the most efficient format of dependency management, and it is also faster. If the selected build system is something like Docker, then the process of building instantly starts and the end product is a Docker image. But if the build system is something like build packs or Nix packs, then we go through 2 additional steps. As we already know, these dependency management systems like build packs and Nix packs, they have 2 phases. The first phase is detection. The second phase is building. As you already know, these build packs and Nix packs, they are just a couple of scripts. And in the first phase, in the detection phase, what they do, they look for the presence of a couple of patterns. If there is a package or JSON in your repository, then it will be flagged as a Node.js app, and the Node.js build pack will take care of that. Same way for Python, it will be requirements.txt. For Rust, it will be something like cargo.toml. But again, it won't be as straightforward. There has been years of research gone behind this. So obviously the actual algorithm is more complicated. They'll try to handle as many edge cases as possible so that they don't flag a application for the wrong build pack just because of a wrong presence of a file. The algorithm is more sophisticated than that. But again, just for the understanding, you can imagine the detection phase as something like that. Then comes the building phase. Now, building is where all your dependencies for your application, for example, for Node.js, npm install. For a Go-based app, it will be Go mod download and Go build and preparing the binary. So all your dependency download step, all your compilation step, and building the final executable step, that will happen in the build phase. But the final output of this whole build pack and Nix pack is basically a Docker image. If we go with the Docker build step, then also we'll get a Docker image in the end. But even if you go with build packs and Nix pack, they also output a Docker image in the end. So after this step, which is the 7th step, the 8th step, we already have a Docker image. That is the output of our previously built system. So in the 8th step, what happens? We push it to a registry. We push it to some kind of registry, either user configured or our own infra, so that if this application is redeployed with this particular version of deployment, then we can just pull this particular Docker image from the registry and we can just create a new deployment instead of doing the whole downloading all the dependency and compiling and creating a binary. We don't have to do all that step since we already have the Docker image in the registry for this particular deployment with the deployment ID. Every time we want to redeploy this particular deployment, then we can do that by pulling the image from the registry and creating a new deployment. Then comes the part of orchestration. Now this can happen with something like Docker Swarm or something more sophisticated and enterprise grade, which is Kubernetes, which is something that Sevalla uses behind the scenes, using Kubernetes for the orchestration for all the servers present in the Google Cloud. But if you want, you can also go with just Docker API based management. If you want to have your own logic for orchestration, then you can have that also. But again, that's not advisable because platforms and tools like Kubernetes, they already provide a lot of features out of the box, and implementing them by hand is not a good idea. In the orchestration step, what exactly happens? A couple of things happen. First is resource allocation. If we are going with Docker Swarm or if we are going with Kubernetes, then a pod has to be created, service has to be created, and for that we have to allocate how much CPU you want to have, how much memory you want to assign, etc. Second step, network config. In case we want to go with Docker's internal networking, it will also have a significant internal networking. And also if you want to integrate a reverse proxy for our networking layer, that will also have a couple of steps here. For example, integrating traffic. Next, volume mounting. Every time we deploy our application, all these things are repeated again and again and not necessarily in the same servers. And because of that, we want some way of persisting the storage and persisting all the data that we have in our application. That's why we make use of Docker volumes for persisting our storage. Then we have port mapping. What are the ports of what all containers that we want to expose outside of the container network? Then we have health checks. Kubernetes has these two important features called liveness probe and readiness probe. A liveness probe basically checks whether your application is running fine or not, whether it has any issues starting up, etc. And then it has readiness probe. Readiness probe is basically whether your particular container or pod is ready to take requests or not. So using different parameters, your orchestration platform decides whether your particular container is alive, it is healthy, and it is ready to take requests from outside the internet. Then at last, we also have environment variables. All the environment variables that you have configured in your platform as a service provider's interface, that gets downloaded, decrypted. In case it is stored in encrypted format, it gets decrypted and it is injected into your container runtime through your orchestration platform in a very secure manner. So those are a couple of things that are handled by your orchestration platform. Of course, it takes care of more things after your deployment. It also services like Kubernetes, they also check for failed pods, and in case your pod has failed, it will create a new pod. And auto scaling things, like if your CPU percentage in the last 5 minutes is more than 80%, you want to scale it to 5 instances. And if it has come down to 30% in the last 10 minutes, you want to scale down to 1 instance. So you can configure things like that so that your orchestration platform can do auto scaling based on your configuration. And that's all about orchestration. Then finally, we have our networking and load balancing. At this step, your platform as a service provider, it makes use of some reverse proxies. So one of the famous ones is traffic. So if we want to take a look at traffic, and you can read here that traffic is an open source application proxy, and you can use traffic for service discovery and routing. You can also use it for API management, API gateway, AI gateway, and API mocking. So primarily, traffic is used for service discovery and management of SSL certificates and load balancing. Those are the three primary steps that a platform as a service provider might need something like traffic for its networking and load balancing needs. These are some things that might happen at this step. One is dynamic routing, which is handled by a reverse proxy tool like traffic. Second is domain mapping. If you have custom domains configured, then traffic can manage that to map your domains to the appropriate pods or containers. Then SSL termination. Traffic can help you create, traffic can help you generate and manage your SSL certificates. It uses a tool called Let's Encrypt behind the scenes for the whole certificate creation and management workflows. Then we have middlewares. Using traffic, you can configure some middlewares for your applications. For example, one famous middleware is if a client makes a request to your domain over a HTTP connection, then that gets automatically redirected to an HTTPS based connection. So that redirection is something that you can configure in your traffic middleware. Other than that, if you want to configure security headers for content security policy or iframe based attacks, that you can configure with another middleware using a traffic middleware. Then you can also configure rate limiting. If you want, you can also add a request ID generator, and there are 100 other use cases for a traffic middleware. Then a reverse proxy like traffic also helps with load balancing, which is again another important feature if you are a platform as a service provider. Depending on how much traffic you are getting, a reverse proxy like traffic, it can manage how much traffic a particular container, a particular pod should receive, and what is the algorithm for balancing the load between different pods and containers, and other things when it comes to load balancing. Then it will also help with health checks. An important one in all this is the SSL certificate management. If you have manually ever generated an SSL certificate and deployed it, you'll see there is a step of domain validation and DNS verification. If you are using something like Let's Encrypt, traffic or any reverse proxy behind the scenes manages these things. For example, the domain validation, the DNS verification, and the certificate renewal if it expires, and things like configuring wildcard certificates if you have use cases for that, or the capability to upload custom certificates. Right? So those are all the things when it comes to the networking side. So while all these things are happening, your platform as a service provider, whichever you are using in this case, it streams all the output from the server where all this installation and configuration step and build step is being executed. All the output of that process, of that terminal process, is streamed into your web browser where we can see in real time all the logs, and that is possible with the use of technologies like WebSockets. So we have a real-time WebSocket open between our web browser and the server where all this configuration and building and deploying step is being executed on. And that's how we can see in real time all the logs. After the deployment is successful, your platform as a service provider also gives you capability to monitor your instances. Monitoring basically includes resource uses, things like CPU, memory, disk, the network input, output, and the historical data about what is all these stats 2 days back, 3 days back. And depending on different conditioning, you can also configure alerting and sending you notifications in different channels. For example, if the CPU usage of your application goes beyond 90% or 95%, you should get a text in your Discord server or your Slack server. And that happens with the use of webhooks. You can configure webhooks so that your platform as a service provider can send you appropriate notifications when the alert conditions are met. Then you can also aggregate your logs, the log drain or aggregation. If you are using services like the ELK stack, the Elasticsearch stack, or services like New Relic, then you can take your license key, your whatever credentials that are needed, and you can configure that in your platform as a service provider so that all your logs from your application that are streamed into your log management provider, something like Elasticsearch or New Relic. After this, when a deployment is finally successful with your reverse proxy managing all your domain mapping and providing a subdomain, and using that subdomain, you can finally access your app over the internet. And that is the whole step from you doing a Git push to your users accessing your application through your domain from all over the internet.